Welcome back to the third video of the 9th lecture in Covidenomics. In this 9th lecture, we've been looking at the economics of price gouging. Last video, we looked at the simple economics, but we also noted that the story may be more complex if consumers view price rises in a disaster, such as a pandemic, to be immoral by firms, and if that would affect their future sales. And we suggested that, in fact, that view may mean that businesses choose not to raise the price during a disaster, even though it would be profitable and possible for them to do so. We're going to explore both the empirics behind that and the theory behind that in this video. First, for the empirics, we're going to draw upon this paper by Cabral and Zhu from Covidenomics, published in May this year, Seller Reputation and Price Gouging, Evidence from the COVID-19 Pandemic. Cabral and Zhu look at three sorts of sellers using the Amazon platform. The first is Amazon.com itself, which accounts for about 40% of the sales on the Amazon platform in the US. The second group are third-party sellers, which are themselves divided into two groups. Ongoing sellers, which are those who were operating before the outbreak of COVID-19 in the United States. So they were operating in the first 2 weeks of January and earlier. And entrant sellers. They were sellers that just come in once COVID-19 has broken out in the US, which is around January 15, 2020. So entrants start their sales after that period of time. They look at three different measures of scarcity. The first measure of scarcity is that they look at stockouts of products on Amazon.com. That's the main seller on the Amazon platform. The second measure of scarcity is that they look at stockouts for incumbent or ongoing third-party sellers on the Amazon platform. And the third measure is one we've come across already, which is looking at Google searches for relevant products. The idea being that if Google searches are higher, that means consumers are finding it harder to find a product, it's searching more, and that is a measure of scarcity. So here's the data on scarcity over the first 4 months of 2020 in the US. And it's for two products, 3M masks and Purell hand sanitizers. And you'll notice that for both Amazon.com and the incumbent sellers, they get pretty scarce pretty fast, and they move in lockstep on both the 3M masks and pretty much so on the hand sanitizer. Notice also that the Google searches also tend to indicate increasing scarcity in both of these products. These two graphs look at the change in prices over time. They're price ratios in the sense that they use the 2019 prices as a base. So a number of 1 here would mean that there was no change compared to 2019. The Amazon.com data down here in blue is given by a scatter plot because Amazon.com had frequent stockouts over time. They then sold again as they got more stock in, stocked out, and so on. That wasn't quite the case for the third-party sellers, so they're drawn as continuous lines until they also run out of stock. The things to note here is that compared to Amazon.com, for both masks and hand sanitizer, third-party sellers tend to set higher prices. But the big difference is the entrants compared to the incumbents. In other words, the sellers who just came in once COVID-19 hit. They tend to sell at around about twice the price of the incumbent third-party sellers. So whilst incumbent third-party sellers are higher priced than Amazon.com, they were leading up to the pandemic as well, the real change is these entrants who come in and they push the price right up, taking advantage of that scarcity. So it's these entrants that appear to be price gouging. Cabral and Zhu, however, want to make sure that it's reputation and not something else driving those pricing results. After all, you could have an entrant in masks or hand sanitizer that is a business that has ongoing sales in other products and cares about its reputation. So what they do in this third diagram is they again look at the price ratios, but now they divide the ongoing and entrant third-party sellers. They divide all the third-party sellers according to their review count. So how many reviews have been put on Amazon about that particular third-party seller? They're divided into those that have a review count of less than 1,000 and those who have a review count of more than 1,000. The idea being that if you have a higher review count, you're more worried about your reputation as reflected by those reviews. And here again, you see that stark difference. For low review count firms, much higher prices than the high review count firms out of those third-party sellers for masks. Not quite as apparent though in hand sanitizer. However, it is suggestive that reputation has something to do with this price gouging behaviour. Cabral and Zhu do some pretty sophisticated econometrics to further analyse the results. They conclude that the results they get tends to confirm the theory. Higher reputation firms are less likely to take advantage of shortages of supply. The result that they get is statistically and economically significant. So for example, in their paper, the price of 3M masks was 2.72 times higher approximately than in 2019. But there was a big difference between the entrants and the incumbents, about 1.6 times at the point of maximum scarcity. Why then do we get this effect of seller reputation? Why doesn't Amazon just raise its price, take its money, and then afterwards lower its price back down again? Economic theory tells us that if we're engaged in an ongoing interaction, then you don't necessarily want to take advantage of your customers or another player in a game. You might deliberately not take advantage of them today, fearing reprisals if you do take advantage in the future. Let's see that by looking at what are called repeated games and the theory behind that. To understand this reputation effect, let's return to a simple prisoner's dilemma game that we've explored a number of times already in these videos. We've got two players, player A and player B. They have two actions that they can take: cheat or cooperate. They're both better off if they cooperate than if they both cheat. There are payoffs in red are player A's, the payoffs in blue are player B's, and if they both choose to cooperate, we're in this square down here, where both player B and player A get a payoff of 20. In contrast, if they both cheat, we're up here in the top left-hand box, where player A gets 0 and player B gets 0. They're both worse off than getting 20 each. The problem here, though, is that if player A believes that player B is going to cooperate, player A would choose to cheat if the game is played only once. In other words, if player A believes that the game is really these bottom two squares down here because player B is cooperating, then player A can choose to cooperate as well and get 20, but if player A cheats, player A gets 30. 30 is bigger than 20, so player A would prefer to cheat. And similarly, from player B's perspective, if they think player A is going to cooperate, well, if they cheat, they get 30. If they cooperate, they get 20. 30 is bigger than 20, so player B will also cheat. So cooperate is not an equilibrium. It cannot be sustained. If they tried to cooperate and only played this game once, then they would both be tempted to cheat. However, if they both cheat, you end up at a situation of 0-0. So in this simple prisoner's dilemma, if you only play the game once, then cheating is a dominant strategy. Even if the two players get together at the beginning and say, look, I'm going to cooperate. How about you? Yeah, I'm going to cooperate as well. Yep, we're both going to cooperate. We agree, we're both going to cooperate. If they actually walk out and play the game, they're each going to think, yeah, if the other player cooperates, I better cheat. I'll get more. Of course, they may also think, I don't believe that player. I think they're going to cheat. And if they're going to cheat, if player A is going to cheat and I cooperate and I'm player B, I get -10. That's terrible. I better cheat as well and at least get 0. So no matter what you think the other player is going to do, you would prefer to cheat. That's the definition of a dominant strategy. Regardless of what the other player is doing, you prefer this particular action or this particular strategy. So it's a pretty strong prediction that in this prisoner's dilemma game, if played only once, that the equilibrium outcome will be cheat, and the players will get 0-0, unlike if they were some way able to get to that cooperative equilibrium. But what about if the players play this game again and again for a potentially arbitrarily large number of times? Then we're going to see that we can actually get cooperate as an equilibrium outcome. To see how this can be the case, we need to introduce this idea of a discount factor, which I'll denote by delta. We can think of this discount factor in at least 2 ways. I'll just do these 2 though for the purpose of this video. The first is we can think of delta as the probability of playing the game again with the same opposition player. So for example, imagine that you play the prisoner's dilemma and then you roll a die. If the die comes up 1, 2, 3, 4 or 5, you play the game again. If it comes up 6, you don't play the game again. So you could imagine playing the game, we rolled a 3. Play the game again, we rolled a 1. Play the game again, we rolled a 5. Play the game again, another 3. Play the game again, there's a 6, we stop. In that situation, delta is 5 on 6. It's a probability that we'll be playing the game again against the same opponent tomorrow. Now, theoretically, that game could go on forever. It is theoretically possible that you could roll a die 100 million billion times and never roll a 6. It's pretty unlikely, but it is possible. So in a sense, we've created an infinite game, a game where it's very likely it's going to stop at some stage, but you can't be absolutely sure. Delta represents a probability it will continue into another round. The second interpretation of this delta is as a discount rate. So let's imagine we literally play this game forever. Every day we wake up, we play it again. Next day we play it again. Next day we play it again. If you've seen the movie Groundhog Day, you know what I mean. We're playing this game again and again, but the future is less valuable than current payoffs. In that case, delta reflects that discounting of future payoffs that we normally put within the interest rate. So under either interpretation, or indeed both at the same time, we can imagine this game played again and again with future payoffs discounted at delta. And if 2 periods away, delta squared, 3 periods away, delta cubed, and so on. So, given these 2 alternative interpretations of delta, we have to think about how does this alter the ability to sustain cooperation within our prisoner's dilemma. To do that, I'm going to pick a very simple strategy. Imagine our players get together and they say to each other, look, we both agree to cooperate. Yep, let's cooperate. But if anyone cheats, if they ever cheat, that's the end of cooperation. We will never cooperate ever again. So if anyone cheats, then they will both cheat every other game after that. So in other words, if you behave opportunistically, if instead of cooperating, player A cheats when player B is cooperating, sure, player A is going to get 30 rather than 20 for that one time. But after that, B says, hey, I just saw you cheat. I am never trusting you ever again. And both players play cheat forever after. So sure, you get an extra 10 for the one period when you behave opportunistically, but you've killed your reputation and you get 0 forever after. Can we maintain cooperation for as long as the game goes on, given that threat to your reputation? So we want to check if these pair of strategies, remember each player is playing cooperate as long as I've never seen any other player cheat, then if I see any other player cheat, cheat forever after. It's a strategy, the same strategy for both players. We want to check if they're a Nash equilibrium. To check if they're a Nash equilibrium, we just need to ask ourselves, would any player want to deviate? In other words, would any player actually want to cheat rather than just cooperate? In other words, would a unilateral deviation from equilibrium be profitable for the deviating player? To check this, let's start off by saying, what do you get if you maintain your strategy of cooperating each period and the other player does the same? Now obviously if both players are always cooperating, they never see anyone cheat, so they never go to playing cheat themselves. So you get the cooperation payoff of 20 every period of the game. But of course, you have to take into account the discount factor. So you get 20 today, then you get delta times 20 tomorrow. Remember, if delta is a probability, there's only a 5/6 chance. With that rolling of a die, 5/6 chance that you'll get your 20 tomorrow. Plus, well, you might get 20 the third time you play. Again, you've got to discount that. Thinking again in our probability terms, you have to have not rolled a 6 twice in a row. So it's delta squared, 5/6 times 5/6. Then, in the fourth period, delta cubed times 20 plus, and you can keep going. This is obviously just an infinite geometric series, and we came across those in the earlier videos in this course. So we know that if a player cooperates today, when she's expecting the other player to cooperate, then her present value of her future payoffs is 20 over 1 minus delta, just simply the sum of that geometric progression. But what about if a player cheats today? Well, that's really easy to work out. Suppose player A cheats when player B is cooperating today. As we noted, player A gets 30 rather than 20, so her payoff is 30 today. What does she get in the future? Well, remember now player B has seen player A cheat, so player B is going to play cheat in every future period. Given player B is going to play cheat in every future period, player A may as well cheat. There's no point cooperating and throwing away 10. So player A will definitely cheat, given that she believes player B will cheat. So player A expects to get nothing in the future. So if player A cheats today, her expected payoff is simply 30. That's her net present value of all future payoffs. So a player will not deviate if the payoff from not deviating is greater than 30, the payoff from deviating. And a little bit of maths tells you that requires this discount factor to be greater than a third. For example, when we were thinking about rolling a die and continuing the game, if the die comes up 1, 2, 3, 4 or 5, and only stopping if the die comes up with a 6, that led to a discount factor of 5 on 6, which is greater than a third. So if player A and player B actually played that game, they would both be able to sustain cooperation until that unlucky roll of a 6 when the game would stop. Note that what we've done here is we've really formalised this notion that reputation matters. that you care about what other players think about you if you think you're going to be interacting with them in the future. So if you're Amazon.com, or if you're an ongoing seller, you may not price gouge, because you know that if you raise prices pretty high today due to a scarcity, due to an emergency, your consumers, your customers, they're going to remember. And they may choose not to buy from you in the future as a form of punishment. And that's completely consistent with the data. In contrast, if you're an entrant, you're a fly-by-night entrant, you simply came in to take advantage of a shortage and then you're going to leave again, well, you don't really care about your reputation. You don't have one. You're really like the player who just cheats because they think they're playing the game once and that's it. Slight technical point here. The strategies that I used here are called grim strategies. Those strategies are that you cooperate, and if you ever cheat once, that's it. Nobody ever cooperates again. They're not the best strategies, and they're not actually very realistic. There's a range of other strategies that you can have. A famous one is tit for tat. In other words, if player A cheats on me today, then I'll cheat on them tomorrow. But as long as they cooperate tomorrow when I'm cheating, then we're all square and we'll cooperate again in the future. And that can still sustain equilibria. It needs a different critical discount factor. But if you can sustain those strategies, obviously that's much better. Someone makes a mistake, they cheat once and sort of, oops. Under our grim strategies, that means you're lost forever. Under tit for tat, it means that you can recover and keep cooperating into the future, which sounds a lot better. So, using repeated games, we can explain people like poor old Matt Colvin here, who, with his brother, went on a road trip and bought up more than 17,000 bottles of hand sanitizer in the US just as COVID-19 broke out. They saw a profit opportunity. They started selling them on websites such as Amazon at highly inflated prices. For example, they bought them for less than $8. They were selling them for up to $70 each on Amazon. And it also explains, the basic economics explains why they were doing that, but the more sophisticated economics explains, well, why Amazon and other web sellers such as eBay shut them down. They ended up donating the bottles back to the hospitals, who really had a better use for them. More generally, economics tells us that this idea of price gouging can be pretty complex. Even the simple economics has pros and cons. The pro is that if the price rises, that encourages an increased supply. The con is that if we're talking about something like hand sanitizer, where we don't want to allocate necessarily by price, we want to make sure it's available for those who really need it, such as healthcare workers. It's better to make sure it's well spread so that lots of people can use it, so that we can really cut down on the risk of a pandemic, not just have one person able to buy lots of it because they can afford it. We know that in those situations, that economics tells us that the welfare effects of price gouging can be ambiguous. It's not an easy argument. But it occurred in this pandemic, and almost certainly it will occur with the next disaster in the future. Thanks for listening. We'll be back next time with Lecture 10.